for today, we will continue our discussion and we will talk about subgraphs. So sub, what does it mean? It means part of. So this is why when we say substring, it means part of a string. When we say subroutine, it means part of a routine. Now when you say subgraph, it means part of a graph. Now if you have two graphs, how to tell that one graph is subgraph of the other one? Of course, the subgraph should have the number of vertices equal or less than the number of the vertices of the original graph. And also the number of edges should be less than or equal to the number of edges of the original graph. By looking, sometimes it is easy to tell that which one is a subgraph of the other one. For example, this one is a subgraph of the other one. By looking, so the eye can see that it is part of. But this is not always the case. Sometimes it is very difficult to see one graph is subgraph of the other one. So how to prove that one graph is subgraph of the other one? First, you pick the subgraph and you label it as H. And then the original graph is, or the mother graph is G. And then if you want to prove that H is a subgraph of G, then you have to tell me the matched vertices. Tell me this vertex, where is it exactly in the original graph? And this vertex, where is it exactly in the original graph? This is one. Second, every edge in here, you have to match it with the corresponding edge for the matched vertex. So I will give them different labels. So I will just give this one label A, and I will give this one label B. So by looking, I need to find the matching vertices of H into G. So V1 is matched to A, and V2 and matched to B. Why? Because see, V1, it has a loop, and A has a loop. So we say that f of V1 is equal to A, and f of V2 is equal to B. So this is a mapping function that will do the mapping between the vertices. After you do the mapping, then you have to go over every edge in H and try to find whether it exists in the original graph or not. So first of all, there is a loop around V1. And what is the corresponding or matching vertex on the original graph? It is A. Do we have a loop on A? Yes, we have a loop on A. So we cover this edge. Now we go to the other edge. The other edge is between V1 and V2. So I have to look for the original graph, an edge between A and B. Do we have an edge between A and B? Yes, we have an edge between A and B. So we have covered all edges. So H is a subgraph of G. Let's go for one more example. Here is an example. The question says, is H a subgraph of G? And this is H and this is G. So if you want to say yes, then you have to show me where is it. Where is H in G? And you know, the eye sometimes cannot tell where is H in the graph. By trial and error, okay, you need to match the vertices to the vertices we have on the original graph. So for all of them incident to two edges, so this one incident to 2, but it doesn't mean that I cannot match B with 5. Because 5 has a 3 vertices, edges. Probably these two edges are one of these two edges. So if you want to write a computer program, then how you do it? Because when you write a computer program, you don't see the picture. You have to work on a systematic way. Human beings think dynamically. But computers, you have to give a procedure to follow to find out whether H is a subgraph of G or not. This will be like a counting problem. First, the computer has to find a matching for A. And how many corresponding vertices we have on the other graph? We have 5. So for A, there are 5 choices. For each choice you choose for A, how many choices remaining for B? It will be 4. And for the next one, how many? It will be 3. And for the next one, so this is P5, 4. And imagine now that if you have 100 vertices, so the running time for this algorithm will not be efficient because it will be factorial. And you know that for factorial, if an algorithm, the running time is factorial, then it is not efficient. But the computer can be made intelligent a little bit by not picking any vertex randomly. I mean, you can pick, for example, for all of these, since their incident edges are 2, then all of these are candidates. But suppose I have a vertex of degree 1 in here. So I cannot match any of these to that vertex because the degree is less. So let us try to see, as a human thinking, where to find H. Now H is a circle of length 4. Can we find a cycle of length 4 on G? By looking, probably by trial and error, there is one. But you need to find it by yourself. So I found one. Where is it exactly? See, if you go from 1 to 3, and then you go from 3 to 2, and then you go from 2 to 1, if you go from 1 to 3, 3 to 2, and you go 2 to 5, and then you go to 1. So this is a circle. So maybe I should write 1, you go to 3, you go to 2, you go to 5, and then you return back to 1. So this is a cycle. So if you want to find the matching vertices, the mapping function, you can say, okay, you started from 1, so you can start from A. So you can say f of A corresponds to 1, f of B corresponds to 3, and f of C corresponds to 2, and f of D corresponds to 5. So this is the mapping function. This is not enough, and finding the mapping is the problem. Once you find the mapping, then what comes next is easy to check each vertex, each edge, sorry. Now if I want to check this edge, for example, it is between A and B, and you know that A is matched with 1 and B is matched with 3. Is there an edge in G between 1 and 3? Yes, there is an edge between 1 and 3. Now between B and C, so this is B and this is C. Is there an edge between 3 and 2? Yes, there is an edge between 3 and 2. Now you go to C and D. C and D, you need to find an edge between 2 and 5, and there is an edge between 2 and 5. And you want to check D and A, so you need to check 5 with 1, and you have an edge between 5 and 1, and this will prove that H is a subgraph of G. Let's go for one more example. In this question, it is asking if H is a subgraph of G. Of course, it's not possible that G is a subgraph of H. Why? Because number of vertices of G is larger than number of vertices of H. So here you have two options. Either you try to find the mapping function to prove that H is a subgraph of G, or try to find what is called an invariant. Maybe one invariant is enough. And what is an invariant? It is a property that exists in one graph. It does not exist in the other graph. So it looks like something informally say differences. Find a property in H that it does not exist in G. So this is our first step before we try to find the mapping function. Let us look for the number of incident edges for each vertex. Here this is 3, this is 2, this is a 3, and this is 2. Now let's go for G. This is 2, this is 2, all of them 2 except 1, which has greater than 2. Now if you want to do the mapping, you need to find a vertex such that the number of incident edges is either equal or greater than. What I mean by this? Now if I want to do mapping, for example, this vertex, then you have to select a vertex that has number of incident edges 2 or above. So you have choices this, and etc. But for this vertex, if you want to match it with any vertex in G, then you have to find a vertex that the number of incident edges of that vertex is either 3 or above. So you cannot match A1 with B1. Why? Because number of incident edges here 3, and here it's 2. So it's not possible that A is the same vertex, if H is subgraph of G, the same vertex as B1. So what can we here find as an invariant? Look, for example, for A1 and A3. Both of them, number of incident edges is 3. But look for all other vertices. Where can I match A1 and A3? I can match A1 with B2 because number of incident edges greater than or equal to 3. What about now A3? I cannot match it with B1 because 2 edges incident here and 2 incident edges. So there is no corresponding matching vertex for A3 because 1 is already taken for A1 and for A3 there is no matching vertex for it. So H is not subgraph of G. So H is not a subgraph of G. Why? Because A1 and A2 in H have 3 incident edges and G has only 1 vertex with number of incident edges 3 and above. And this disproves that H is a subgraph of G.